Section 8.5 of Young and Freedman's University Physics is about center of mass. Center of mass is a useful concept for when you're talking about a collection of particles that are moving together within a certain frame of reference, or maybe you're talking about a body, maybe it's a weird rock whose mass is not distributed evenly within that body. And so the concept of a center of mass is helpful if you have a collection of particles or a strange body that is not uniform, and you're wanting to analyze the motion of that collection of particles, the momentum of that collection of particles. In such cases, it's helpful to conceive of them in terms of a center of mass. For example, one of the examples in this section is you're talking about a rocket that's been fired, and the rocket explodes. So it started off as a single body, but now it's several particles. Another example in this section is I believe it's a water molecule, where you're trying to find the center of mass between the hydrogens and the oxygen. So it can be useful when you're talking about the motion of something or the momentum of something to be able more or less to treat that object or collection of objects as a point. The center of mass is the kind of the point where if you were to take all that chaos or all of that kind of unevenness, if you could reconceive of it as a point at a particular location, that's the center of mass. Okay, what is the equation for the center of mass? The equation for the center of mass is a mass-weighted average position. So basically, you put this collection of masses, say, within some sort of coordinate frame. So you basically put an x, a y, maybe a z framework on it, and you say this is I'm going to treat this point as the origin, and then I'm going to identify where this collection of particles are in relation to that origin, and then I'm going to call that r. So r is a vector, so you have r x component, r y component, potentially r z component, and cm stands for center of mass. And so what is that point, that center of mass at r? Well, it's going to be a mass-weighted average position. The average part comes from the fact that I'm going to divide all of those mass times different positions by the total mass. That's what makes it an average, because when I'm done with adding up the components, I divide it by the total mass. That's what makes it a average. It's a mass-weighted position because I'm taking the position of each particle in this collection, and I'm weighting it by multiplying the mass of each particle by the position of each particle, the vector position of each particle. So I have particle 1 from the firework has exploded. I have particle 1 with mass 1 at position 1, and then I have particle 2 with mass 2 at position 2, and so forth and so on. And so if I want to find what the center of mass is, I basically multiply the masses of the individual particles by the positions of the individual particles and divide it by the total mass of the system. And of course you could do this also with a body like an unevenly distributed mass in a rock. The problem there is, of course, is that you're going to have to do an integral, that's basically treating an infinite number of points or something along that line. But anyway, this chapter's not, or this section doesn't go into that difficult position, that difficult kind of stuff. So I can multiply both sides by the total mass, and here I have another way of conceiving this. The total mass of this collection of particles times the position of the center of mass equals the masses of all the individual particles multiplied by the positions of all the individual particles, or to use summation notation, the sum of all the individual masses times all the individual positions. That's going to give us the total mass times the center of mass. So that is kind of the fundamental point of this section. Now I can integrate both sides. I mean, not integrate. I can take the derivative of both sides of these equations. Of course, mass is a constant, so it doesn't do anything. It comes outside. But the derivative with respect to time of these positions is going to be the velocity. And so if I take the derivative of the vector position in relation to time of the center of mass, that's going to give me the velocity of the center of mass. And then I'm going to get the velocities of all of these individual particles. So basically, total momentum, what is momentum? Momentum is mass times velocity. And so by taking the derivative of m times the center of mass position, I get mv, which is the total momentum of this collection of particles. So it turns out like this. mv, and I should have had probably center of mass cm down here under the v on the far left. That way you would have known that it was the total mass times the velocity of the center of mass is going to equal the masses of the individual particles times the velocities of the individual particles. And again, I should have had the arrow over the v1, v2, v3 so that you would know those are vector quantities. And so I take all the masses of the particles, multiply it by all the velocities of all the particles, and I'm going to get the total momentum of this system, which is the total mass times the velocity of the center of mass. So this again is helpful. For example, if I wanted to analyze the trajectory of the center of mass of that firework, even though the firework is exploded and is in pieces, I can still analyze the trajectory of the center of mass of that collection of particles. There are a number or a couple of significant implications or kind of associated truths with what we're talking about here. One is because of Newton's third law that for every action there's an equal and opposite reaction, internal forces within a body cancel each other out. That when I'm considering the force on a collection of bodies, it's only the external forces that affect the total motion. So the forces associated with a collection of particles, or the forces associated within that abnormally formed rock or whatever, the internal forces cancel each other out. The only forces that are significant with regard to analyzing the trajectory of that collection of particles are external forces. So that's something to keep in mind. Here's the way Young and Freedman put it. When a body or collection of particles is acted on by external forces, the center of mass moves just as though all the mass were concentrated at that point, and it were acted on by a net force equal to the sum of the external forces on the system. So you can ignore any internal forces in that system if you're trying to analyze the way the forces might affect a collection of particles or a strangely formed body and so forth. Here's another fun one. This is really fun. If a projectile like that firework explodes into a bunch of fragments, the center of mass continues on the original trajectory. This is interesting. There is an example in this section that plays this out. That if once that firework explodes, you have all kinds of different pieces going in different directions. But if you were to go back to that first equation, the total mass times the position of the center of gravity equals all the individual masses times all the individual positions, you're going to find that and then if you took the derivative of that to get the momentum, you're going to find that basically even though it's now a collection of particles, the center of mass will continue on the same trajectory as if it didn't explode at all, which is quite fun. And like I said, there are examples in here. There is the example of the center of mass of a water molecule and so forth. So this is section 8.5 on the center of mass in Young and Freedman's University